The first question that arises is, what is radiation? Radiation is a method of heat transfer, so first it is better to answer the question, what is heat transfer? Heat is energy, so heat transfer is a way to transfer energy. Heat transfer is caused by temperature difference, so whenever the temperature is different in two different sides, the heat is transferred from the hot side, higher temperature to the cold side, lower temperature Now, this heat transfer can be done in three different ways. When the fluid is still, heat transfer occurs by conduction between fluid layers. For this reason, for solid bodies that are always stationary, conduction heat transfer always occurs. And about convection, actually it happens when a fluid is moving on a solid surface, and in this case, heat transfer occurs by convection between fluid layers. But there is a third method of heat transfers that is less paid attention to, and that method is radiation heat transfer. Now, I want to provide comprehensive information about this heat transfer method in this training course, so stay with me. Here the question arises, when should we go for radiation? Let me first define radiation. Actually, heat transfers that occurs through electromagnetic waves is called radiation. The main cause of this heat transfer method is the vibrational and rotational movements of molecules, atoms, and electrons. Therefore, these vibrational and rotational movements are equivalent to the temperature value. An increase in temperature leads to an increase in the rate of radiant heat transfer. In fact, radiation depends on temperature according to Stefan-Boltzmann equation, which I will explain in a few moments, so that the temperature has the fourth degree or power. This means that when the temperature reaches the fourth power, its value becomes significant, and the higher the temperature, the more visible this fourth power of temperature is. So now we know when we are allowed to go for this method of heat transfer. When the temperature is high, it can be said that the radiation heat transfer method prevails and it can no longer be ignored compared to the conduction and convection heat transfer methods. This is every surface of objects has its own radiation at any temperature, which is often ignored. But when the surface temperature is very high, it can no longer be ignored and the heat transfer method will be dominant, such as radiant heat transfer from flame, or cases where explosion and combustion occurs, or processes related to and etc. Now, let's go to some important relationships in the field of radiation. Considering that radiation occurs by electromagnetic waves, we express the relationship between wavelength and frequency. These two parameters are inversely related to each other, and they are related to each other by the speed of light. For this reason, the speed of light is used because waves travel at the speed of light, and this speed is equivalent to 2.99 times 10 to the 8. We go to Einstein theory, where it claims that the transfer of energy due to the emission of radiation waves is equivalent to the transfer of energy packets, called photons. Each energy package has a frequency equal to nu, so the energy of each of these packages is given by this relation. In this regard, H is equivalent to Planck's constant, which is equal to 6.625 times 10 to the minus 34. Since H and C are constant, then the energy of the packets or photons is inversely related to the wavelength. Now look at this picture. In this graph, you can see a range of different wavelengths. According to the graph, X-rays and gamma wave have a short wavelength but very high energy, so it can be said that they are destructive waves, while radio waves and microwaves have a long wavelength but low energy. As you can see, light or visible waves are between the wavelength of 380 nanometer and 750 nanometer, which is between ultraviolet and infrared waves. I want to examine two terms in the topic of radiation: blackbody radiation and gray radiation. Blackbody is the most complete energy absorption, and the most complete energy emitter related to emission in a specific wavelength. In other words, at a given wavelength, no body can emit more energy than a blackbody. Now, consider the Stefan-Boltzmann equation I have mentioned before. This relationship expresses the radiation power emitted by the blackbody per unit of time and per unit of area. In this regard, sigma represents Boltzmann's constant equal to 5.67 times 10 to the minus 8. In addition, we have a concept called emissivity, which expresses the ratio of the energy emitted by a body to the energy emitted by a black body at the same temperature. It is always expressed by the term epsilon. Now we go to the concept of gray and non-gray radiation. Gray level radiation occurs when the radiation properties are independent of the radiation wavelength, while in non-gray radiation, the radiation properties depend on the wavelength. So, in a case of gray radiation, the emission is strongly dependent on the temperature, while in the case of non-reflective radiation, it is also dependent on the wavelength, and the relationship of emissivity is expressed as a spectral emissivity. In other words, it can be said that in gray mode, energy emission occurs at any wavelength, while in the non-gray mode, the energy emission takes place in a specific range of wavelengths. Now, I want to talk about a new concept, irradiation. Actually, emissivity is equal to the radiant energy reaching a surface and is denoted by the symbol G. This energy can be divided into three different modes. Some of it is absorbed by the surface, some of it passes through the surface, and some of it reflects off the surface. The ratio of the energy absorbed by a surface to the total energy received by that surface is equivalent to the absorption coefficient, absorptivity, which is denoted by the symbol alpha. The ratio of energy reflected from a surface to the total energy received by that surface is equivalent to the reflectivity, which is represented by the symbol rho. And the ratio of the energy passed through a surface to the total energy received by that surface is equivalent to the transmitivity, which is represented by the symbol tau. Naturally, all these coefficients have a value between 0 and 1. So, since the sum of these energies is equal to the total energy received, the sum of these coefficients will also be equal to 1. Now, if the surface is opaque, naturally no energy passes through the surface. So, the received energy is divided into two modes of absorption and reflection. We also have a law called Kirchhoff's law in the subject of radiation. This law asserts that the energy radiated or emitted by a surface at temperature T is equal to the total absorbed radiant energy received from a black body at temperature T. So it can be concluded that epsilon is equal to alpha. In the discussion of radiant heat transfer, we sometimes deal with a concept called view factor. Visibility coefficient is for times when we focus on heat transfer between two surfaces. In fact, heat transfer between two surfaces is related to the angle of the surfaces in relation to each other, in addition to the radiation properties of the two surfaces. This is where we need to introduce a new concept called visibility factor. This visibility factor is only dependent on the geometric condition of the two desired surfaces. Of course, we make several important assumptions to calculate the visibility factor. First, the radiant heat transfer happens completely uniformly on the entire surface. Second, the space between the two surfaces doesn't absorb and reflect the energy exchanged between the two surfaces. In other words, there is no intervening environment between the two levels. Now, suppose that radiation rays are transferred from a surface called I to a surface called J. The ratio of the energy received by surface J to the energy emitted by surface I is expressed as Fij. According to this definition, the numerical visibility coefficient will always be between 0 and 1. For example, for the present figure, if Fij is equal to 1, it means that surface J is completely covered by surface I, whereas if Fij is equal to 0, it means that two surfaces don't see each other at all. In addition, we have two important laws in the subject of the coefficient of views. First, there is the law of inverse coefficients, which states that AIFij is equal to AJFJi, and second, there is the law of addition, which states that the sum of visibility coefficients in a closed space is equal to 1. In other words, if we have a completely closed surface, all the energy produced by the surfaces collide with each other. Even we can express the expressions Fii, it means radiation between different points of a single surface. Now, if you pay attention to this figure, you can see that Fii is equal to 0 for flat and convex plates, while its visibility coefficient is non-zero for a concave plane. It's time for ANSYS Fluent software for implementing computational fluid dynamics CFD projects. This software has many capabilities for numerical simulation with various study subjects in the field of fluids and heat transfer. One of the interesting features of ANSYS Fluent software is the use of the radiation module. When you activate this module, you will encounter different ways of defining radiation heat transfer. These methods are Rosseland P1, discrete transfer radiation model, DTRM, surface to surface, S to S, discrete ordinate, DO, and Monte Carlo, MC. In addition, this module has the ability to apply solar load. Solar load includes two methods of solar ray tracing and solar irradiation. So, with this module, you can define the radiation of solar rays on the computing domain, and you can also define the radiant heat transfer in the computing domain in different ways. In this training course, we intend to introduce all these radiation methods. Before we start a comprehensive tutorial on the radiation module, we suggest that you familiarize yourself with some important terms related to the radiation model. A complete familiarity with these terms will help you understand the topics related to the radiation module training in the software better and more easily. So, we introduce these terms and concepts one by one. Diffuse surface, it is called a surface whose radiation properties are independent of the wave propagation direction. In simpler terms, it is a surface where the propagation of waves will be scattered in all directions. If the effect of scattering in radiation is considered, the radiation is forced to deviate from its straight path, and this deviation from the path is caused by the effect of non-uniformity in the environment it passes through. For example, in the reflection of radiation, the rays are deflected from their intended angle. And about optical thickness. Actually, it is a measure to check the ratio of incoming or incident radiation to transmitted radiation. The thicker this optimal thickness is, the more radiation it receives and the less it passes through, so the light is easily absorbed, while the thinner it is, it receives less radiation and passes more, so the light passes easily. Participating effect, actually basically any medium that absorbs, emits or scatters radiation is called a participating medium. When we talk about the contribution effect, it means whether this environment affects the quality of radiation rays or not, while the non-participating medium is assumed to be a completely transparent space like vacuum, which doesn't have any effect on radiation rays and doesn't absorb, emit or scatter radiation. Refractive index. Actually, it is equivalent to the ratio of the speed of light in a vacuum to the speed of light in the environment it enters. This parameter is indicated by the letter N, solid angle. If we look at an object at a certain distance from a point, the angle that the object makes with respect to the starting point is called a solid angle. In other words, this special angle is the magnitude of the object from our point of view. Of course, we also have a series of other important terms that we have previously explained. Terms such as emissivity, blackbody, irradiation, gray and non-gray surface, and etc. Now, it's time to introduce different methods in the radiation model one by one. For now, we are going to have a general introduction of these methods and not go into details, so we will have a comparative review. Each method has a series of advantages over other methods, and on the other hand, there are a series of limitations in its use. Adequate knowledge of these advantages and limitations will help us better understand the difference between these methods. First, I start with the discrete transfer radiation model, DTRM method. The first advantage of this method is that it is relatively simple. Second, this method has the ability to increase the accuracy of the solution by increasing the number of rays. Third, this method can be applied in a wide range of optical thickness. On the other hand, we examine the limitations. The first one assumes that all surfaces are diffuse. Second, it doesn't consider the effect of scattering. Third, this model assumes that gray radiation occurs. Fourth, solving a problem by defining a large number of rays becomes heavy for the system CPU. Fifth, it is actually incompatible with non-conformal mesh or sliding mesh. And sixth, it is incompatible with the parallel solution process. The next method that I want to introduce is the P1 method. We intend to state the advantages and limitations of this method compared to the previous method, DTRM. The first advantage it has over the DTRM method is that it can be solved with low CPU. The reason is that the radiative transfer equation, abbreviated as RTE, is expressed as a diffusion equation. The second advantage of this method is that it takes into account the scattering effect. Third, for applications such as combustion where optical thickness is high, this model works relatively well. Fourth, this model can be used for complex geometries with curved coordinates. On the other hand, we discussed the limitations of this model compared to the previous method here now. First, this method, like the DTRM method, considers the surfaces as diffuse. Second, this method is limited to gray radiation or non-gray method, with non-gradient model. Regarding the non-gradient band model, we will give comprehensive explanation below. Third, it makes the work heavy for the CPU. Fourth, it is possible that the accuracy of its solution will decrease when the complexity of the geometry is high or if the optical thickness is small. Fifth, it tends to overpredict the radiative fluxes caused by sources or thermal wells. Sink or source, Now it's time to introduce the Rosseland model. Actually, its main advantage over the P1 method is that it doesn't solve the additional transport equation for the received radiation. Therefore, compared to the P1 method, it performs the solution faster and requires less memory. On the other hand, we point out the limitations of this method. The first limitation of this method is that it is only used for optically thick media with high optical thickness, for example, for an optical thickness higher than 3. Second, this method can only be used for the pressure-based solver and is not available for the density-based solver. One of the most widely used methods in the radiation model is the discrete ordinates method, DO. First, we try to express the advantages of this radiation method. Its first advantage is that it covers a wide range of optical thicknesses. In this sense, it can be said that this method is widely used in various problems from surface-to-surface radiation to radiation in combustion problems. Second, this method provides the possibility of solving radiation in semi-transparent walls. Of course, we'll talk about opaque and semi-transparent walls later. Third, this method has a moderate and reasonable computational cost for the usual angular discretization, but it requires moderate memory. It is time to examine the limitations of this method compared to previous method. First, this method is limited to gray radiation or non-gray radiation using the non-gray model. Second, this method is not supported when using granular, liquid-solid, Eulerian multiphase flow. Third, if we don't use DO energy coupling in this method won't be supported when using multiphase models. Of course, in the continuation of the training course, we'll provide complete explanations about the energy couple method. Another method of heat transfer is surface-to-surface S2S radiation. The main feature of this method is that this method is suitable for modeling radiation heat transfer inside a chamber or closed space without the intervention of the material environment or participating media. Second, this method works faster in terms of time per iteration. But this radiation method also has limitations in its use that we point out. First of all, this method is one of those radiation methods that consider surface as diffusers. Second, it only implements the gray radiation mode. Third, the storage and memory required to solve this radiation model increases rapidly with the increase in the number of levels. Of course, it is possible to minimize the levels of the model by using the ability to create a cluster, and hence it reduces the speed of the solution. Regarding the concept of clustering, comprehensive training will be given later. Fourth, it is in use in radiation problems involving the participating environment. And fifth, this model doesn't support semi-transparent boundaries. The last radiation method I want to explain here is the Monte Carlo MC method. The first feature of this method is that it can solve a wide range of optical thicknesses from areas with thin optical thickness or transparent areas to areas with thick optical thickness or diffusion areas such as combustion phenomena. Second, this radiation model can perform accurate Gaussian solutions. And the third advantage of this method is that it is more accurate than other available radiation models, but in the same proportion, the computational cost increases. But there are some limitations in using this radiation method. First, all the desired physical quantities are calculated as surface or volume averages. The next thing is that there are things that are not actually supported by this model, things like two-dimensional models, transient solution, moving mesh, discrete phase model, DPM Eulerian multiphase models, VOF and mixture and Eulerian, and a few others. When it comes to fluid behavior analysis, as usual, we have to go to the transport equation. At the time of defining the radiation model, the software must solve a general radiative transport equation, RTE, for the computational domain. This equation applies to all radiation methods, but according to the chosen method, this equation can be changed and some of its terms can be removed. Look at the equation in the picture. The parameters in the radiative transfer equation are introduced. Parameters such as location vector, direction vector, path length, scattering coefficient, absorption coefficient, radiation intensity, Stefan-Boltzmann constant, refractive index, fuzzy function, local temperature, space angle, and scattering direction vector. The radiation intensity depends on the location and direction The index of refraction is taken into account when considering radiation in an opaque medium. Things like absorption coefficient, dispersion coefficient, refractive index, and etc. are defined in the section of determining the desired material properties in the software. After we had a brief introduction of all radiation model methods and compared their advantages and limitations, now the question arises as to which method to use in our modeling. In other words, when to use each method. First of all, we must say that each of the mentioned methods has a series of capabilities that are naturally used in some specific problems. That is, we can name applications in modeling for each method. However, sometimes we want to apply the radiation model to some problems where we cannot determine which method is more appropriate. In such cases, we should look for a series of criteria or factors. We'll mention some of these criteria. The first criterion is the amount of optical thickness, which we have already talked about. We consider optical thickness equal to alpha L, where alpha is equivalent to the absorption coefficient and L represents the appropriate length scale for the computational domain, for example, equivalent to the diameter of a cylindrical combustion chamber. If the value of alpha L or optical thickness is much larger than 1, P1 and Rosseland method are the best option to choose. Of course, if this value was slightly greater than 1, the P1 model should be selected, and if this value is slightly larger than 3, the Rosseland method is a cheaper and more efficient method. The second criteria under consideration are the scattering and emissivity coefficients. If we use the scattering coefficient as a criterion, the P1, Rosseland, and DO methods are radiation models that consider the scattering effect, while the DTRM method ignores this effect. If we consider the emission coefficient as a criterion, the Rosseland model is not sensitive to the emission or emissivity of the wall. The third criterion is checking the effects of suspended particulate effect. The presence of suspended particles in the space means things like dust, smoke, and pollutants, water droplets, and etc. The suspended particles can affect the quality of radiation in the space under investigation. Among the radiation methods studied, only P1 and DO models can consider the range of radiation between gas and suspended particles. And the fourth criterion we check is the presence of mirror walls. The meaning of the mirror state is that when the radiation beam reaches the surface of the desired wall, its reflection is only in one direction and at the same angle as the incoming radiation. Among the radiation methods, only the DO radiation model allows a specular reflection, like smooth mirrors. The fifth criterion is the effect of the presence or absence of the participating environment in the radiation space. Regarding the participating environment, we have already provided the necessary explanations. Now, if radiant heat transfer occurs inside a chamber with a non-participating environment, the S2S radiant method is considered the best proposed option. Of course, we should point out that the S2S method may also be effective in a model that has a participatory environment, but it is not always efficient. To benefit from Master CFD services including simulation, consultation, and training, visit our website www.mastercfd.com and contact us via info@mastercfd.com.